while SMILE is fresh on our minds, since we just had that nice plug about it from both Jeff and Adam, I will make a couple of comments. So as we heard, our colleague Jinfa Yin will be here to speak later in the week. And besides the fact that he developed this SMILE reconstruction method, and this was his first software development project, which is incredibly impressive. Jinfa is also an incredibly skilled and gifted spectroscopist who measures the most beautiful spectra that I ever see. So he will have a point of view about NUS from the spectroscopist's point of view. And so I think that will be valuable to those of you who are doing a lot of experimental work and setup to hear what it is he has to say. And in terms of the speed of SMILE, when he set out to develop this method, he wanted to apply it to the largest of 4D data sets that when they're fully reconstructed were 100 gigabytes or more in size. So from the first principles, he worked very hard to optimize the details, especially in terms of how it uses multiple threads to do all the computations in parallel whenever that's possible. And so as we'll see, it's remarkably fast. Now what you see on the screen here is a kind of collection of different elements that are commonly performed in all the steps from taking raw spectral data to the spectrometer and extracting some kind of useful information from it. And during the course of our discussions and demonstrations today, we'll see examples of just about all of the things that are listed on this slide. Now, as has already been mentioned, many similar presentations have already been posted in different places, including on the NMR Box sites for previous workshops. You can find streaming videos. Some of these have also been posted online. And then furthermore, for NMRPipe in particular, there's both a LinkedIn group and a groups.io group that you can join and ask questions of me and of the community about this stuff. Now, also, after the last lecture that I made today, there were some questions in chat that I didn't see and didn't get a chance to address. And the question in chat had to do with the reliability of spectral heights and volumes when you use non-uniform sampling. So we did see this example from the data, which is extraction of volumes from small molecule proton carbon data. And in these examples, which were reconstructed by IST, NMRPipe's IST, and SMILE, all of the results give comparable accuracy for the volumes. Here's another example. This is intensity versus intensity. And in blue is intensity versus intensity between two replicate spectra reconstructed by the Fourier transform. So in other words, the same spectrum measured twice on the same sample. And in pink is drawn the intensity versus intensity plots of a fully sampled data compared to its IST reconstruction. And as you can see, there's beautiful linearity. And we can apply these same methods, and this is actually specifically what the question was about. We can apply these same methods to pseudo 3D relaxation series. And so here's an example. We can do either independent 2D reconstructions, one plane at a time. And in this case, if we subsample down to a density of 25% NUS, if we only do independent reconstructions of each 2D plane in a series, the results we get aren't really great. But we have methods to reconstruct the data as a whole, sort of like a complete 3D experiment. And when we do it that way, we can also get excellent recovery, nice linear recovery of the intensities. So here's what things look like. Let's turn on a little laser pointer. Excuse me, conventional 2D reconstructions here, 3D pseudo 3D reconstructions here. So intensity correlation better than 0.98 across the full range of intensities. So by and large, for typical kinds of NMR data, these methods are very linear and reliable. And as we also mentioned, one of the ways you can test this is to resample your own conventional data and see what it would have behaved like if it was a non-uniformly sampled spectrum. And we're going to see how to do that a little later. So first, what I will do is make a little introduction of the NMRPipe software for the folks in the audience who haven't used it before or aren't familiar. And then we'll stop with the slides and actually poke around with some software. Now, during these discussions, I won't be able to see if there are questions because of the way I have my screens arranged. So I want you to feel free to unmute yourself and just ask your question out loud, okay? So let's get to NMRPipe. Typical steps of spectral processing for a given dimension. We apply a window function and scaling of the first point. We apply a zero fill, a Fourier transform, and a phase correction. And that's pretty much a recipe for 90% of spectral processing. In order to do spectral processing like this, the NMRPipe system, the engine for performing Fourier transforms in the NMRPipe software, takes some important concepts from the Unix computer operating system. One concept is the idea of a filter. A filter is some program that takes input, changes it in some way, and produces output from the changed results. So, for example, we can imagine a Fourier transform implemented as a filter that takes as its input a series of time domain vectors and produces as its output a series of frequency domain vectors. Very straightforward. And that continues to the next critical concept that we adopt from Unix, which is the idea of a pipeline. A pipeline is two or more programs connected together in a series so that the output of one program is used automatically as the input to the next program in the series. So for example, we can have one program that applies window functions to all of its input vectors, and its output is a set of vectors where the window functions have been applied. And then that can be sent in a pipeline to another program that applies a Fourier transform to all those vectors, and so on. So it's a beautiful and simple concept, and it allows us to reorganize processing schemes as lines in a Unix shell script. And so the learning curve for NMRPipe becomes becoming familiar with the individual commands for performing different kinds of processing functions like window functions, zero fills, and Fourier transforms. And here's some examples. Each of the processing functions in NMRPipe has a short abbreviation. SP is a window function, ZF is a zero fill, FT is a Fourier transform, PS is a phase correction. And along with each of these functions, we generally have one or more command line arguments that say specifically what the function should do. So for example, for phase correction, we have command line arguments for the zero and first order phase corrections. And there are numerous processing functions like this. Some common ones are solvent subtraction filters, linear prediction, Hilbert transform, which generates imaginary data from the real part, extraction of a particular region of interest, exchanging the dimensions of a data set, or performing baseline correction. And once we have a set of processing functions like these, we can put them together and build multidimensional processing schemes. For example, we can achieve three-dimensional processing by a sequence of three different pipelines. One pipeline, which reads all the vectors from one dimension of a time domain input and sends those down a pipeline to be processed, gathers up the processed results, and writes them out to an intermediate result. And then we follow that by another pipeline that now reads data vectors from the next dimension of that previous result, sends those down a pipeline to be processed, and then gathers up that result and writes it to another intermediate file. And then finally, the data vectors from along the third dimension of that previous result get read in, sent down a pipeline, processed, and then accumulated and written back to a result. And that's all we need to convert a scheme like this one to achieve multidimensional processing. And there are all sorts of fantastic things we can do with schemes like this. So for example, we can insert transpose functions, 2-dimensional or 3-dimensional, inside the processing scheme, and these rearrange the data along the way so that we can have a single pipeline that processes 2 dimensions or 3 dimensions of the spectral data. In practice, all of these can be performed just by reorganizing commands in a Unix shell script. So the way in which we build processing schemes in NMRPipe is to build Unix shell scripts that have all the details of interest in them, and we will see how to do that. Now, this is all well and good, shell scripts, but of course we have to look at the experimental data. We want to visualize it, test the effects of parameters and so on, perform peak detection. So we have an interface in the NMRPipe system called NMR Draw, and that's going to let us look at raw and processed data, choose phase correction parameters, and so on. Now, what you see here is an annotated and typical Unix shell script for processing 3D data. And what you see is a pipeline of commands. There we go. So this long stretch of commands is one long pipeline. And at the beginning of the pipeline, we have a program that reads data in from a time domain data set. And at the end of the pipeline, we have a command that writes the data out to a process data set. And in between, we have a list of all the processing functions that we want to apply and the parameters for those processing functions. This little backslash at the end of a line means the command is continued on the next line. And this little vertical bar character is the Unix pipeline character. It means the output of one line is sent automatically as the input to the next line. Okay. So in this processing scheme, we have a solvent filter, a window function, a zero fill, a Fourier transform, a phase correction, extraction of a particular range of chemical shifts. This is a script for amide detected data, so we extract an amide range of chemical shifts. And then a 2D transpose, which exchanges the rows and the columns so that the remainder of the commands now process the next dimension, the indirect dimension, which also gets a window function, a zero fill, a Fourier transform, phase correction, and now transpose back again, and then a baseline correction to baseline correct the directly detected dimension. So the advantage to this is now we have a complete recipe for how to go from raw data to processed data with all the parameters built in. So this is a complete reproducible record that shows how you went from the raw data to the finished process spectrum. So that's very valuable. On the downside though, if you don't know anything about NMR signal processing and have never written a Unix shell script, this is terrifying, right? It is incredibly terse and cryptic and difficult to understand. So over the course of time, we have tried different ways to make building these processing schemes a little easier and more automated. And so now we have individual single commands that will auto-generate a script like this. So for example, all the details in a script like this can now be captured with a command like this one. So we have these new commands, basic FT2, basic FT3, and so on, that build complete commands, complete processing schemes from a small number of parameters and insert as many parameters in an automated way as possible. So generally speaking, typical processing, we don't need to do very much more than put in phase correction values and a region of interest if we have one. And now furthermore, if we want to do fancy things like adjust the scheme so that it includes extrapolation by linear prediction, all the details stay the same, except we add a few additional arguments that explains what we want to do. In this case, we add some extra options that say we want to do mixed forward-backward linear prediction. Now suppose we want to instead use the methods that we talked about today to do extrapolation by non-uniform sampling reconstruction instead of linear prediction. In NMRPipe, we call that extrapolation NUS zero filling, and we can add that to a processing scheme just by adding this option, NUS ZF, and we can choose whatever particular reconstruction method that we would like to use to perform that extrapolation. For example, IST, SMILE, NESTA, and so on. So super easy. Part of the motivation for building the scripts this way was to support a particular workflow for multidimensional NUS data. And what we recommend as a workflow for non-uniformly sampled data, and we'll see some very specific examples of this soon, is that the way to work with this data is to first do an ordinary Fourier transform. Process it in the same way that you process conventional data, and sort out the details of getting the phase correction settings right and the Fourier transform operations set up correctly. And only once all of those details are settled do you go through and do a reconstruction with IST or SMILE and so on. And so to make this easy, we added additional scripts that use the same kinds of arguments as the Fourier transform scripts. So if I have NUS data, I can process it with a regular Fourier transform command like this. And when I'm ready to do a complete IST reconstruction, I just used a different script, IST3D, that takes pretty much all the same arguments. If I want to do SMILE instead, parameters are more or less the same. It's just a different script name. And for the Sierra and SMILE signal subtraction that we've seen before, all the details are the same. So we just use the same kind of processing arguments that we would use for reconstructing an ordinary spectrum, but we also have a list of the different regions whose signals we would like to model and subtract. So it's about as easy as it could be. So all this stuff we can do from the command line when NMRPipe is installed, but what we're going to do in addition is to see a new graphical interface, which is part of NMR Draw, which will allow us to do all of this processing and all of this script generation automatically within a graphical interface and without the need to edit a script. So that's going to be pretty cool, I think, right? Yeah. Let's try it.
So Frank, one question. Yeah. So you mentioned about doing the trial processing before we get to the IST, let's say.
Yes.
So do you advise that as the pathway, even if I have a 4D data set?
Yes, absolutely.
Okay.
Absolutely, I do. And I will I will explain why in a bit.
Okay.
And demonstrate. And 4D is a perfect example. Depending on the size of the final result, the 4D reconstruction could take hours. If you do it with NMRPipe's IST, which is the slowest of all the reconstruction methods, it could easily take a weekend. So you want to have all the reconstruction details settled before you sit down and do a complete reconstruction. And I'll show you how to do that and show you why it's profitable.
The main question I have there, the reason I asked is the most important thing is even though if I collected the data, okay, I should supposed to use the -19 180, let's say, as a phase factor for the indirect dimensions. Many a time you might think that you have to adjust it a little bit, but this has to be done quote unquote interactively. So there's no other way for me to do it other than generating a spectrum. So as you pointed out, I have to do it with the raw 4D data and probably look at the plane and edges of phase, correct? There's no escaping that as far as phase correction is concerned.
Right. So the thing is, of course, if you do a regular Fourier transform, usually the individual planes themselves are not so informative or useful. So the thing to do, and this is built into the software, we'll see it, is that you do this inspection on the basis of projections of the result.
Right.
And those are generally good enough to choose phase correction parameters.
Okay.
And with 4D data, depending on what kind of data it is, you'll be shocked to see how good an ordinary Fourier transform often looks. So, but we'll see some 2D and 3D examples. And there is a 4D data set somewhere in the NMRPipe demo archive that you can have a look at. Okay, so let's see. I'll talk about the specific location of this demonstration data a little bit later when we actually do some hands-on demos. But to start with, we're going to look at a humble 2D proton nitrogen spectrum of a small protein, okay? That's a good place to start. This is data that was measured on a Bruker spectrometer. So before we get into too many details, we're going to talk in tedious detail about the procedure for converting data from the spectrometer format to the NMRPipe format. Because there are a few details of this that if you get them right early on, when you first work with the data, things will be much easier downstream when you have multiple spectra to work with. So everything that we do in NMRPipe for conversion and processing is done by Unix shell scripts. So we have to build a shell script to convert the data from the spectrometer format to the NMRPipe format. And we have to build one or more shell scripts to process the data from the time domain into the frequency domain. And that's what the remainder of our discussion is going to be about. We have different graphical interfaces to help us build these conversion and processing scripts, to execute them and to look at the results. The command that I'm going to use for converting Bruker format data is the command Bruker. So I'm going to type Bruker at the command line inside this data directory that has the Bruker parameter files, the Bruker SER file, and the Bruker pulse program file. And when I do that, I get this little graphical interface. Okay. So NMRPipe nomenclature. The directly detected dimension is called the x-axis, and the remaining dimensions are the y, z, and a axis for 4D data. The first thing that we do in this interface is just take a look at it. So we have 3 columns for the 3 different dimensions of the data. And in this interface, we're going to specify details about how many points are in each of the dimensions and what the chemical shift calibration information is. And the NMRPipe scheme for calibrating chemical shifts is based on the idea that the center of the directly detected dimension is at the water signal. And so, with that prior knowledge, based on the temperature of acquisition, this interface will calculate what the chemical shift of water should be at that temperature, and then it will set the center position of the directly detected dimension accordingly. So if you look closely at this interface, what you will see is that for the x-axis, for the directly detected dimension, it says center position is H2O. And up here, where it says temperature, it says take the temperature from the parameter file of the spectrometer. So that's how things start. Now, when I read the parameters, this interface is reading all the spectrometer parameter files. It's determined that this is a two-dimensional experiment, so now we only see these two columns here. It's determined that the measurement temperature was 297 Kelvin. It calculated the chemical shift of water at that temperature as 4.773 and put that value in here. Now, depending on where the pulse sequence came from, whether it's a homemade one or an official one, many of these parameters, even simple parameters like the spectral width of the indirect dimension, may not be recorded correctly inside the spectrometer parameter files. And so it's often the case that we need to adjust these parameters by hand. And that's the purpose of this graphical interface. In this case, though, it's pretty much everything is set up the way that we want it to. All these values are correct. So there's nothing more that I need to do, except that I'm also going to turn on a checkbox here. And the checkbox says, run NMR draw in process mode after conversion. I'll turn that checkbox mode on. And now I'll save the conversion script on the disk and execute that conversion script. Okay, so here is my time domain data. Lower the contour levels a little bit. So what you see over here is a display of the time domain data. And on the left-hand side is a processing script generation interface. So let's talk first a little bit about the basics of NMRPipe and the NMR draw graphical interface. Up at the top is the command panel for NMR draw, and it has several different pull-down menus. For example, the mouse pull-down menu has a list of all the different commands that activate the mouse to perform one task or another. So if I set the command 1D horizontal from the mouse menu, that gives me a vertical or horizontal cursor bar in the spectral graphics area. And what I'm going to do is drag with the mouse, and I can move that cursor through the data and see different 1D vectors. Now, whenever NMR draw is active in doing something by way of the mouse, if you look at the top border of the program, the top border tells you what the left, middle, and rightmost mouse buttons will do. And generally, there'll be one set of functions when the mouse pointer is inside this spectral drawing area. And there'll be another set of functions when the mouse pointer is out in the borders where the axis is drawn. So, for example, according to this message, if I use the middle mouse button outside, I can change the vertical scale of whatever slice I'm looking at. And if I use the right button outside, I can change the vertical offset of whatever slice I'm looking at. So very easy. And you might also notice as I change which vector I'm viewing by dragging the mouse cursor, if you look at the command panel up at the top left, you'll see that the slice number in the indirect dimension, the y-axis, is being updated in real time as I drag the cursor. And if I want to, I can point with the mouse to this text entry area and actually type in a specific number, like 1. So here's the first 1D slice of the data. Here's what it looks like. And if we want to process this spectrum, we can go to the process menu and choose a command called auto process 1D. That provides a predefined Fourier transform with a window function, zero fill, and so on. And the program recognizes this is amide detected data, so it just extracts the amide region and shows that here. And now if I'd like to interactively phase correct this data, I can go to the command panel, and there's a button that turns interactive phasing on. So I'll click that button here. And then there are sliders that adjust P0 and P1. I can just slide this slider with the mouse, or I can click on one side of the slider or the other to increment or decrement the phase value by a little bit. And you can see that whatever phase value is being applied is listed in the command panel. And I can also type a particular number, like 90, what have you. So interactive processing. Now let's turn our attention to this 2D processing window here. And it has parameters for processing the directly detected dimension and the indirect dimension and some other special details. Let's not change a thing. Let's just create a processing script with no adjustments at all, no phase corrections, no anything, and execute this script. So here's the process result that we see. And there's a button here that lets us see what kind of scheme the script produced, the button edit script. So here's what it is. Here's our NMRPipe processing pipeline. And here is the basic FT2 command that generated this scheme. So we have complete documentation of how this scheme actually came to be. And there are a couple of things that you might notice. So one thing I notice, and this is a common circumstance, that the two halves of the indirect dimension are rotated so that the center of the spectrum is at the edges instead of the middle where it should be. This means that the data requires a particular manipulation of the signs of alternate points before the Fourier transform is performed. This is common in states TPPI experiments. Sometimes this sign adjustment is built into the pulse sequence. Sometimes it isn't, and we have to do it during processing. This is one of those cases that we have to do it during processing. So over here, I'm going to check the checkbox for the indirect dimension that says rotate the two halves of that indirect dimension. And now I will create a new processing script and execute it. And here's our process data. So one other thing now, if we actually looked at 1D slices, we see that they're not phase corrected. All right. So back in the processing interface, there are values that let me put in numbers for 0 or first order. I'm just going to use a menu that says auto phase the directly detected dimension instead. And I'll create a new script and execute that one. The auto phasing is being performed. And there's the process spectrum, and it's beautifully phased. So we didn't have to do any much special. And here's the script that was created. So that script has a command that performs the auto phasing and it extracts the value. And then that value gets inserted in the processing scheme at the appropriate place. So in practice, the only thing we needed to specify for this data is the Fourier transform options for the indirect dimension. And all of the other details were handled automatically. Now, this spectrum is already super beautiful and narrow, but just for demonstration purposes, let's do a few interesting things. So for example,
question.
Yes,
Wes Pavlovsky has a question. Can autophase be accessed from the command line?
yes, it can. So let's look at that briefly. So if I just say basic FT2 with no other options, here's the spectrum that we get. So it has the wrong Fourier transform mode in the indirect dimension, and it's not phase corrected yet. So now I'm typing that same command, but adding an option that does the sign alternation Fourier transform in the indirect dimension. And now here's the result we have. So the peaks are in the right place, but they're not phase corrected yet. And now if I want to add auto phasing, as you suggest, I can just say XP0 auto. And we wait a little while because the auto phasing is performed on the a big band from the 2D spectrum that encompasses maybe 20 or 30% of the full spectral width. So it takes a little while to do.
This is very cool, Frank. Thank you for doing that.
Oh yeah, you're quite welcome. It's a great question.
Frank, while you're waiting for that to process, I noticed that on the command line, you backed up and put in the auto phase flag and parameter before the alternation flag. Does the order matter, or is that just
the order does not matter? Yeah, I just did it for conceptual reasons.
Gotcha.
I like to keep the parameters for the different dimensions in order when it's possible, but it's not a requirement at all. So let's see what spectrum we generated, and there it is, right? It's pretty beautiful.
Frank, can I ask you on the phasing part you just showed, even in the 1D version,
Yep.
so can you talk a little bit about the pivot which you use for the phase correction interactively?
Sure.
There's definitely a lot of confusion, but I am confused even today.
Yeah.
So
That's a good question, and I'm going to postpone it till the next data set that we look at, because that data set actually needs a phase correction in the indirect dimension. So it'll be a better test example for answering that question.
Okay,
Okay?
thank you. Sure.
Yeah,
Thank you.
very good. Okay, so we're back here, and I'll set things up to the way they were before. So when we left off, we had a regular Fourier process spectrum, and phasing had been performed automatically.
Hi, Frank. I have a question for you. What about referencing, like for the proton dimension, the DSS or whatever your reference compound is?
That is a very good question. So in this case, as I showed during conversion, the default referencing scheme references the data according to the center position of the directly detected dimension, assuming that that is the chemical shift of water. Okay, so there are 2 or 3 other schemes that you can use. For example, if there happens to be a reference peak in the data, let's see, you can use cursors and point to that peak. And in the file menu here is a command called calibrate axis. And that gives us a calibration window where we can enter the specific chemical shifts that the spectrum should have at that position. So that's one way to do it interactively. If you want to do it under script control, there's a script called ref2d.tcl. And the way this script works is that we give it a range of chemical shifts. So for example, if it's a DSS peak, it would be a range of chemical shifts that are right around 0. And what this routine will do is perform peak detection in that region and assign the chemical shift of the largest peak to whatever value you say. So we have methods to set or change the chemical shift calibration interactively from inside NMR Draw, and we have ways to do it under script or software control from the command line. Does that sound right?
Yes, perfect. That's exactly what I was looking for. Thank you.
All right, awesome. So let's see, and of course I ditched our result from before. This stuff can be saved, by the way, these parameter settings. So to get back to where we were, so there's our spectrum. This is a regular Fourier spectrum. So now let's go to the processing interface and turn on linear prediction. And we can set the linear prediction mode or the linear prediction order, but for now I'll just generate a script and execute it. And we will shortly see our linear predicted results. Now, these peaks are already really sharp, so you can see that they are sharper now after linear prediction, but they were already pretty sharp before. So this LP result is very nice, but just to be wild and crazy, as an alternative, let's try one of these other methods. So for example, I'll choose NMRPipe's IST, and now instead of extrapolating the data by linear prediction, we'll extrapolate it by IST reconstruction. So I'll generate a new processing script and execute it.
Frank, while IST is running, good time to bring up a question. We've had a little bit of a side discussion in the chat window about IST algorithms. One of the things that I pointed out is that not all IST algorithms are the same in terms of where they exit the iteration. And so, for example, some of them exit right after the replacement step, which guarantees that the mock data that they generate, so to speak, that gets typically then it gets Fourier transformed to get the reconstructed spectrum, always exactly matches the measured data.
Right. That's a great point. So now that you mention that, I will show something about that.
Well, here's my question. Does yours exit there, or does it exit after the thresholding step, or?
You have a choice.
Oh, okay, excellent.
Yeah.
So the reason it came up was because we were the slide you showed about the nonlinearity, and I was pointing out that not all IST algorithms have the same nonlinearity.
Right.
In fact, the ones that tightly constrain or exactly force the mock data to match the measured data would be the ones that are most highly linear.
Right. So the result that you saw is from the other approach. Okay. So NMRPipe's IST by default generates the spectrum directly. And so if you were to inverse transform the data, the parts of the time domain that were measured originally do not necessarily correspond exactly to the result that you would get. And
Is there a way of getting the degree of match calculated or
yeah,
reported?
sure, you can do that. Now in NMRPipe, the default method, we call it IST, and the method that restores the original time domain data is called RIST. Okay, so you can choose between them. Generally speaking, the default method, which generates a spectrum directly, is better at artifact suppression, whereas the method of restoring the original time domain points will tend to give slightly broader but rounder peaks. So no big surprises. The whole situation is kind of strange, Jeff, because these reconstruction methods are used to suppress sampling artifacts, right?
Yeah.
And then once you do that, we subject them to an ordinary Fourier transform scheme and add a new set of artifacts on top of them. So for that reason, we developed this option of doing the IST reconstruction directly without having to resort to going back to the original time domain data, which gives you a mixture of partially suppressed non-uniform sampling artifacts and a new set of artifacts from the final Fourier transform.
Yeah.
All that said, for 90% of the data that you look at, it won't make any difference at all. And we will see examples of exactly that. So here's the IST results. Let's do the RIST results. And you probably won't see much of a difference. Actually, let's expand the region here. So that's an IST result. And the iterations in this implementation of IST are set to stop automatically when the size of the anticipated artifacts is down around the level of the noise. Okay, so let's look at those same peaks now. And you might see a little bit of a difference. So they are just a little bit fatter and rounder than they were before. And just for the heck of it, let's try Smile, which is super fast. And we'll try that on some 3D data soon. So that just zooms by. And also nice, beautiful round peaks. Okay. So that is 2D reconstruction. Now we
Frank,
have
does that,
oh yeah, go on.
by default, does that just extend the data one time?
Yes. So you
Okay.
could, there are parameters in there that you can change, but it doubles the number of points by default.
That's fine. Okay, that's cool. Thanks.
Okay. So we have generated some different non-uniform sampling schedules already for this data to show you an example of performing resampling with this interface. So here's the interface in resampling mode, and it actually says this is the non-uniform sampling resampling mode of the interface. Okay, and the processing parameters are all the same, but now at the bottom we have an additional set of options, including the name of the non-uniform sampling schedule that we'd like to use. So I will try a 50% schedule. And I will turn on auto phasing. And we already know for this data, we have to rotate the two halves of the spectrum. And now I will update. And we have now, when we work with non-uniformly sampled data, we get one script that performs a regular Fourier transform, as we talked about, and another script that performs the full NUS reconstruction. So let's execute the regular Fourier transform scheme. And the software automatically takes the original measured time domain data and resamples it according to the sampling schedule that we gave it. The auto phasing step is being performed now. And here's the processed version of the data. So this is regular Fourier processing of the non-uniformly sampled data. So it's full of artifacts. But if I raise the contour levels a little bit, you can actually see the spectrum is pretty legible. And we can also see that the phase correction is okay, and the Fourier transform options are okay. So now that we're convinced that all these other settings are reasonable, we can execute our non-uniform sampling reconstruction method. And now the IST calculation is happening.
While it's calculating, how do you get the side panel to show an NMR draw again?
A beautiful question. There are two ways. One is in the conversion interface, there is this checkbox, run NMR draw in process mode. When you do that, it actually inserts a line, it's a comment, it inserts a line in the conversion script that shows how to run NMR draw to get that process window to appear. And to do it requires two steps. First, you have to include the command line option -process. And second, you have to include explicitly the name of the time domain data. So that's how that part works. You can do it. Let's see. So this is what it looks like to do it for regular data. For the resampling mode, it's the same, except we have an additional option, resample. So that's how you do it. The process switch, the name of the FID, and the resample switch if you want to do resampling.
So Frank, tying into what we start, so this is exactly the way I can try to test the user's fully sampled or uniformly sampled data to demonstrate to myself or the user saying, hey, look at what's happening here, correct?
That's exactly right.
Okay.
Yeah. Yep, that's exactly right. So here's our IST reconstruction. And let's see, actually. We have a utility called spec versus spec. will give it these two spectra and let's see how it does. So they're not scaled to each other. All right. Not scaled. Spectra. Oh, it's the fully sampled data. Come on. They're not the same size either. Okay, I'm ditching this part of the demo. Anyway, so that is how we can do resampling inside this interface, and we'll see examples of this for 3D data as well. And so just as a final test, let's use a sampling schedule that we know should deliver a bad result, just to see what it looks like. So I'll choose a schedule that resamples at 12.5%. And we'll use, let's say this time, let's use the reconstruction. Nesta is also super fast.
So Frank, if I understand correctly, you are taking a fully sampled raw data, resampling it to 12.5%, and then reprocess it with the reconstruction, correct? That's what we're doing.
That's exactly right.
Okay.
Yeah. So the resampling has been done, and now the reconstruction is being performed. 14 little seconds, nice and fast. And the result is pretty good considering it's only 12% sampling. So there you have it. I'm impressed. So when you show someone a result like this and say, if you could do this with 12%, you could be pretty comfortable at 40 or 50%. We'll be okay. And actually, in the days that I worked at Agilent and we introduced these methods that would easily allow any pulse sequence to be converted to non-uniform sampling, we actually found several university and pharma facilities that made all of the routine 2D measurements non-uniform sampling by default.
Yeah.
And they didn't even tell the users. They just set it up that way, and all the routine measurements were acquired. So for a particular class of molecule, when you have an idea ahead of time what the most complicated molecule that you are likely to see, and you're not sample limited, so you don't think that signal to noise is going to be an issue, for all of these routine measurements, you can do this pretty safely in a standard way, and all of the reconstruction methods give nice results. Okay, so that is the 2D case. Let's look at a 3D case. So same details, only this 3D example that we're going to look at together, this is variant data. So the conversion interface to work with it is called variant, but the details are the same. We read the parameters, adjust them by hand if needed, and save them as a script. We can run NMR draw in the process mode after we want. And so that's what I will do. Now I will say save script and execute script. Silly me. I also have to select the input for this. Okay, so here is the first plane of our time domain data, and the processing interface is roughly the same as we saw before, except it has additional options because this is 3D data. So I'm not going to do anything. I'm not going to change a thing. I'm just going to create a processing script and execute it. So no phase corrections, no Fourier transform options. Okay, and now here's the process result, and I can page through it and see peaks that are in different places, and they're obviously not in phase. In the processing interface are buttons that let me look at the XY projection of that 3D result and the XZ projection of that 3D result and the YZ projection of that 3D result. Okay. So obviously I see when I look at the XY projection that the data is definitely not phase corrected properly in the directly detected dimension. So let's stick in auto phase for this dimension and update the script and execute it. Okay, so now the process version looks like this when I scroll through planes. If I look at the XY projection, I see that the data is not phased in this indirect dimension, the carbon dimension. But if I look at the XZ projection, the proton nitrogen plane, I see that that is nicely phased. So we have the proton dimension nicely phased and the nitrogen dimension nicely phased, but we don't have the carbon dimension nicely phased. So what do we do about it? Well, we had a question: when you do interactive phasing, how do you choose pivot points? And what does it all mean? How do we do this work in NMR draw? So we want to phase correct vectors from the vertical dimension of this data. So I'm going to go to the mouse menu and choose the command 1D vertical. And that'll give me a vertical cursor. And I can move it to different positions in the spectrum. Like let's say this one. Now, suppose I would like to look at more than one vector at a time when I perform the phase correction. Well, in the command panel under the 1D menu, there's an option called Append 1D. That's going to keep this particular 1D vector on the screen. And now I can go elsewhere if I want and look at data from other positions in the spectrum. And this gives me the ability to get as many 1D vectors as I want so that I have signals across the full spectral width in order to most effectively choose phase correction parameters. To choose phase correction parameters for data like this, we start by positioning a pivot point. And so the window tells me I can use the leftmost mouse button outside. And if I move the leftmost mouse button, you might see there's a pair of very small arrow cursors. So that's the pivot point. I will point the pivot to one peak in the data, like this one here. And then in the command panel, I'll adjust the 0 order phase until the peak at that pivot point is phase corrected. And once that's done, I'll adjust the first order phase so that everything else in the data is phase corrected as closely as possible. So these are the parameters I get. So by I have minus 131 and 184. If I phase correct this thing by I could probably do a little bit better, we'll see. But generally speaking, if you see a situation like this, where the first order phase correction is close to 180, that's a clue that the experiment was probably set up so that the phase correction value is exactly 180. So if you're interactively processing spectra and you see that, the first thing you should do is try specifically with a 180-degree phase correction and adjust the P0 value accordingly. Okay, so that's how it goes. Now I happen to know for this particular data, which has a block secret shift in it, that the phase correction for this dimension should be minus 135, 180, and there's actually even a menu entry for this. So we can choose it interactively or choose it from a menu, but now I'll update the script and execute the script. Okay, processing is finished. The 2D planes from this dimension look good. The XY projection looks beautiful. The XZ projection looks beautiful. And therefore the YZ projection is very nice too. And in addition to looking at the projections, there's also a button in this interface that will automatically generate a strip display of the data. So let's look at that.
Frank, can I just interrupt
Yes.
before you move on that
Yep.
phase correction? So when it comes to the pivot selection, is there a clear understanding or recommendation of where the pivot should be with respect to the offset at which I collected the data on that dimension?
I'm sorry, can you ask that question again?
The pivot point which you selected interactively in this in the demo, you chose somewhere around 175 ppm for the carbonyl axis, right? Before you did the phase correction by hand.
Yep.
Now, is there a rule or an understanding or a theoretical rationale that where the pivot should be vis-a-vis what is the offset of the axis, that particular axis?
Okay. Now I understand. Thank you for being patient and explaining it to
Oh,
me.
sure. Thank you.
Oh, I deleted the result. Hold on just a second. Get back to where we were. So this is a great question, and the answer is subtle, but fun to know. Good to know. For a case like this one, where we have the equivalent of minus 90, 180 phase correction, if there were no phase correction at all, it would mean that the phase of the peaks changes linearly from one position to another, which is what we saw in the originally processed version of the data. Now, the linearly dependent phase correction comes from the fact that if you delay by a certain amount of time, that delay is an increasing fraction of a cycle of each frequency. So the delay has a big impact on low frequencies and a correspondingly smaller, I'm sorry, the other way around.
The other way around, yeah.
Yeah, a smaller impact on larger frequencies.
Correct.
So that phase correction gets larger in magnitude as you move away from the center of the spectrum.
Right.
But the question is, along the lines of what you asked, where is the center of the spectrum? Where's the zero frequency position?
Exactly.
So the zero frequency position is at point n/2 + 1 of the spectrum. Okay, so
Okay.
if there are 256 points that go from point number 1 to point number 256, the zero frequency position is at point 129. So if you'd like to move the pivot to that exact position, that's the number that you would type in here. So you can set the pivot numerically or set it according to, interactively according to the mouse.
Now, this is the in quadrature mode. In the real dimension, the actual quadrature mode is because there are two detectors and so on. In the multidimensional NMR, we generate the real and imaginary part with the state CP kind of manipulation, right? So
That's
when you
right.
said 256, you mean 256 complex points or 256 of either real or imaginary point?
Yes, I mean 256 of either real or imaginary points.
Okay. Okay. So if I have a state CP where I collected data in the carbonyl dimension, let's say I have 256 complex points, where is going to be my center on the carbonyl axis?
Okay, so in that data set, you have 256 complex points, so 128 reals and 128 imaginaries.
Right.
But when you process the data, you will zero fill it. So let's say you zero fill it once. That means you'll have 256 real points and 256 imaginary points.
Right.
And in a typical processing scheme, you actually delete the imaginary part. So
Right.
you're left with 256 real points, just like in this case, actually.
Right.
So in that case, the zero frequency would be 0.129.
I see. Which pretty much comes to the center of the axis.
It's the center plus 1.
Center plus 1. Okay.
Yeah, it's the center plus 1.
But then why did you choose your pivot to be on the upfield somewhere around 180 in the demo you did?
That's a great question. So putting the pivot in the center will only let you phase correct the spectrum if there's no additional phase correction beyond what's caused by the initial delay.
Oh, I see. Okay. Great. Thank you. That is very important.
It was an interesting discussion. I'm glad somebody in the audience is interested in a detail like this.
No, this is very critical. Wow.
And now it's archived for the entire NMR box community. So you just did everyone a great service.
Carve it in stone, everyone.